Hello everyone, thank you for listening to my presentation today. My name is Rachel Siegel. I am a graduate research assistant at the University of Vermont. I am presenting on Project 4.4 Bridge Stream Network Assessments to identify sensitive structural and hydraulic parameters for planning flood mitigation. A big thank you to the University of Vermont and the TIDC. Dr. Dewakar, Dr. Rizzo, and Dr. Bombleys, as well as everyone from the Vermont Agency of Transportation for all of your help and contributions to the project. Funding for this research is provided partially by the Transportation Infrastructure Durability Center at the University of Maine under the grant from the U.S. Department of Transportation's University Transportation Centers program. The Vermont Agency of Transportation provided a match to this project, which is greatly appreciated. The Technical Advisory Committee of this project includes personnel from the Vermont Agency of Transportation and the Vermont Agency of Natural Resources. This project is included in the University of Vermont Transportation Research Center research portfolio. I will start the presentation by going over the motivation for the research, then go over the project objectives, discuss some of the research progress, and finally the next steps and some conclusions. To begin, I'll go over some of the motivation for the research. On August 28, 2011, Tropical Storm Irene came northwards through the Connecticut River Valley, depositing 4 to 8 inches of rain across Vermont. The storm resulted in infrastructure damage, including damage and failure to more than 300 bridges, damage and closure to over 500 miles of state highway, and damage and closure to over 200 miles of railway in Vermont alone. This led to many state and local stakeholders posing questions and concerns for their current and future bridge projects. How can infrastructure withstand more frequent extreme flood events of greater magnitude? And how will previous, current, and future projects affect others up and downstream within the river network? The northeastern United States is experiencing a trend of more frequent and persistent extreme precipitation events. As a result, infrastructure must now be able to withstand more extreme flood events of greater magnitude. This leads into the current objectives for the project. The first objective is to develop transient hydrologic models of low, medium, and high gradient river corridors with significant transportation infrastructure. Using the Hydrologic Engineering Center's River Analysis System, or HEC-RAS, models were made for the river corridors capturing low and medium gradient systems using Otter Creek and the Black Creek. A hydrologic model has also been made for the Mad River, which captures medium and high gradient areas. The second objective is to perform sensitivity analyses around infrastructure within the hydrologic models and observe the bridge stream network response. For example, if a bridge was expanded, how does that affect the river's velocity up and downstream? Where is the river flooding, and how deep is the inundation? And what type of land is being flooded? Using this information and comparing it across all three models, we can perform a risk assessment at the river network level for state and local stakeholders. Evaluation of whether the simplified risk assessment methodology can be applied to other stream bridge networks with similar geographic and climate conditions in New England and elsewhere is the third objective of this research. So what has been done so far? As mentioned earlier, a HEC-RAS model was made for the Otter Creek. This model was made by a previous graduate student, Matthew Trueheart, with the funding from the Vermont Agency of Transportation. The upstream and downstream boundaries for this model were 2 USGS stream gauges in Rutland and Middlebury, Vermont. The study area was predominantly a low gradient, and 12 road and 8 rail bridges were observed, as well as several overflow bridges and more than 100 culverts. From this portion of the project, a simple flow chart was made that identified potential structure and network sensitivities within the bridge stream network. The other model being focused on in this presentation is the HEC-RAS model for the Mad River. The study area for this location is between Warren and Moortown in Vermont and has multiple sections varying from a medium to higher gradient. 16 road bridges are being analyzed, as well as over 100 culverts in the area. Unlike Otter Creek that had 2 USGS stream gauges, the Mad River only had 1 gauge at the downstream boundary of our model. Field work was done to collect depth and velocity data in the upstream boundary in Warren. This information, along with bathymetry data collected by Du Bois and King, was input into HEC-RAS. From there, a computational mesh was made and the hydrograph information was entered to calibrate the results to Tropical Storm Irene. As mentioned previously, there is fieldwork being done to continuously confirm the calibration for the upstream boundary. At Warren Falls, we placed a HOBO pressure transducer to record absolute pressure every 15 minutes. This is then converted to depth within the software, and as frequently as possible, velocity measurements are being collected using a Pygmy stream meter. These measurements are being used to make a rating curve that will be used to calibrate the Mad River HEC-RAS model for other storm events like the one that took place on Halloween in 2019. Collecting data like this allows us to make necessary adjustments to hydrograph inputs that are required to calibrate the models to reflect what happened in real life as closely as possible. The Tropical Storm Irene hydrograph was then scaled for varying storm events, that is, 25, 50, 100, and 500-year storms. The numerical model was then calibrated for each of these storm events. All of these had Nash-Sutcliffe values ranging from 0.94 to 0.98, producing reliable results. With the models calibrated, we are now beginning to analyze results. These results include analyzing flood inundation boundaries and the types of land that are being flooded. Here we can see Otter Creek and the area that is inundated during Tropical Storm Irene. The most common types of land that were flooded were woody wetlands, pasture and hay, and cultivated crops. In the Mad River, we can see right off the bat that it is a much smaller inundation area, and the types of land that are flooded are also different. Instead of empty woody wetlands, the major area that is flooded is pasture and hay, followed by cultivated crops and deciduous forests. These areas could potentially have a higher risk for those involved in agriculture. Another factor that can be assessed when observing inundation is if there are any bridges that are being overtopped. Knowing the parameters for overtopping can help stakeholders better plan and prepare for future projects, reducing risk in the long term. Here's a close-up image of the different storm inundation boundaries around the Waitsfield Covered Bridge. You can see that the Irene and 500-year boundary, which are the red and orange lines, closely overlap each other, and this is further enforced by the very close overlapping in their hydrographs. Not all storm events closely overlap like this along the entire river corridor, but in this case it is important to know that only extreme events like the Tropical Storm Irene and the 500-year storm event results in overtopping this bridge. The green line is the low chord of the covered bridge, and the Tropical Storm Irene and a 500-year storm event are the only scenarios that overtop the bridge, making this a location of interest, but do not necessarily make it a high-risk location depending on the parameters being looked at. Instead of extracting inundation areas, another way to observe areas of interest is by running the results in the model and observing the velocity. These are examples of the Mad River model showing velocity results during Tropical Storm Irene in various up and downstream locations along the river corridor. Each one of these locations features a type of infrastructure such as a bridge. These locations all vary in depth, inundation area, and velocity profiles, and the higher velocities make each site an area of interest due to the potential risk that comes from high velocities. Making adjustments to the structures, such as raising elevation or expanding deck width, could have attenuating or mitigating effects for the velocity profiles within the network. This particular site has one of the highest velocity profiles within the model calibrated for Tropical Storm Irene. Taking a closer look at this area, which is the Warren Covered Bridge, we can see that all of the storm inundation boundaries are very close together. There is very little flooding and no overtopping. However, the bridge is narrowing the river corridor, forcing a high velocity spot slightly downstream. This could potentially pose a high-risk situation for other infrastructure and projects further downstream. By performing different scenarios, for example, widening the bridge, we can determine if this high-velocity section can be mitigated. In conclusion, I'll talk briefly about our next steps. Total inundation and land area will be compared across all hydrological models. This will tell us the different infrastructure and different surrounding populations that could potentially be at risk for varying storm events. Running different scenarios by expanding and elevating different types of infrastructure within the models, we can observe how factors like inundation area, velocity, and combinations of different factors can affect the river corridor and other infrastructure further upstream and downstream. Using this, we can build a risk assessment to further identify high-risk locations and infrastructure for state and local stakeholders. We hope to apply a wrapper methodology and programming, which is currently under development as part of another project. This wrapper will allow us to automate our sensitivity analyses to run hundreds of scenarios, such as lengthening a bridge, lowering an approach road, adding a culvert, etc., to optimize a desired set of outcomes such as reduced velocity, no inundation approach roads, and so on. We will also take a deeper look at these similarities and differences across the 3 study sites to infer conclusions that could be applied to other sites. Thank you for listening, and I'm happy to take any questions you may have.